Okay, ladies and gentlemen, welcome back. Today we are, for a change, not so much going to talk about fuzzing, but instead we're going to talk about debugging. One thing that happens when you're using a fuzzer is you're creating these long and possibly obscure strings and files and input that cause your program to crash. And then you find actually out that it crashes, and then the question is, what is it that caused the failure? And today I'm going to present you one technique that helps tremendously with that. This technique is called delta debugging, and its aim is to reduce an input to the minimum that actually causes the failure. And for this, I'm going to go into a simple program, a simple example program that actually exposes a bug that occurs with particular inputs. So let me share my screen here so that you can actually see things. Okay, let me go right into the middle of things. So you can now see a little program in here. And this program is called the mystery runner. And this mystery runner, let's take the class out here, has a function. It takes an input and it does some mysterious things on this input. And under certain conditions, it fails. Boom. So now I made this up specifically for you such that it is difficult to read and that it's not immediately clear what this program actually does. You can, of course, go and find out what this actually is and find that out. But in reality, ladies and gentlemen, you're not going to have just one single function. You're going to have hundreds and hundreds of functions, and you have no clue what's actually going on. If you already have narrowed down things to a single function, you would already be pretty happy. So what do we have here? So let me just import stuff here. I'm importing runner. I'm defining this whole thing, and now we have a mystery runner. And this mystery runner is something in which I can feed arbitrary inputs, say, what are we going to do? I'm bored today. Make this hello world of fuzzing. Okay, here we go. And this is an input which happily passes. However, there are inputs which actually fail. I'm going to be lazy and I'm simply going to copy in one of our inputs that I have prepared earlier. So, and I'm going to call this failing input. The name already suggests something in here, I know. So here's my input. Failing input is whatever this long string, which actually comes from a fuzzing input. Here we go. And as I said, the name already suggests something because I already know, because I have prepared that well in advance. I can, if I run this on the failing input, failing input, there we go, then I get a failure. So this string, hello world, works. This string, which is a weird combination of letters and symbols, no letters actually, okay, which is a combination of digits and symbols, this one fails. Okay, and it has to be something with these conditions that we have in here. Okay, so now you wonder, okay, I have all this, I have this big string that fails, but what is in there that actually causes the failure? And for this, we're going to go and I'm going to import a magical class here from our reducer class. Import delta debugging reducer. This is a reducer class, which means that it's set to bring the input to a minimum. So now here we have it. And what am I going to do with that? This delta debugging reducer is a automated debugging technique which can automatically take a runner and automatically find out a minimum input such that it fails. And this is actually very, very easy to use. So what we do here is we built a delta debugging reducer, and I put in a runner as we do with our fuzzers just as well. So I instantiate this. Here we go. This all works. And this DD reducer has a single important method, which is named reduce, which we can invoke. And now I feed in the failing input. Poof! And now with that, we're going to find out what part of this input actually causes the failure. And within less than a second, it tells us it is this. It is an opening and a closing parenthesis. And we can actually verify this because we can run our mystery runner on this minimal input, and we find that it also fails. So now, instead of having this tremendously large input, which we have up here, which also causes us lots of trouble during debugging because, well, we have to go through the individual steps and we have to process all these characters and figure out what do all these characters do and everything. Now we have a much smaller input, and this much smaller input, of course, A, is much easier to debug because, well, if we step through the program, we only have 2 characters to process. Second, it's also much easier to communicate because I can tell you, well, if you have an opening and a closing parenthesis in your program and this opening parenthesis precedes the closing parenthesis, then the program fails. And we can actually now look into the code. What is it that's happening in here? It turns out that these octal characters, I wonder how often you folks have seen octal characters before, but they exist. These octal characters over here actually are the opening parentheses, and this is the closing parentheses. We look for their indexes in the string, and if there is an opening parenthesis, and there also is a closing parenthesis, and the opening parenthesis precedes the closing parenthesis, then the whole thing fails. Okay. Now that we know what the 0017 plus 0031 actually means, now we can understand what's going on in here. So this is pretty convenient. Rather than having a big string from fuzzing, just have it shrink down to a minimum. Question is, how does our delta debugging reducer do this? And for this, we can go and run a special logging thing in here. So we can set a keyword log test equals true. There we go. And now we have the same reducer as before, but now with logging enabled. And now we can give it the failing input. And now it's going to show us what it actually does. What we're doing in here, and you see what's happening now is it actually runs a couple of tests on the failing function. Namely, what it does is it takes the entire input. We see it starts with a space and it ends with a hash character, and it starts by feeding this entire thing into the test and finds that the test fails. What does it do next? It does binary search. It goes and takes the second half of the input, or more precisely, it removes the first half from the input and see whether this fails too. So taking away parts of the input and seeing whether they still fail. It first does so with the first half, but this passes. Then it does so with the second half of our input, but this passes too. This is actually this is the second half of the input over here, and this is the first half of the input. So precisely, it first removes the first half, and then it removes the second half, which means that the other half remains. Okay, so binary search in this case doesn't help us that much, because both halves actually pass. So what does delta debugging do then? It removes smaller parts of the input, and these parts get smaller and smaller again. So what it does next is it takes away the first quarter of the input. And taking away this first quarter of the input, which in our original test is this part here up to the colon, if it takes away the first quarter of the input, then it fails. And when it fails, when it has reduced the input to a new failure, it starts going again with the first half and the second half and so on. And it keeps on removing smaller and smaller parts until it finds a failure. And it keeps on removing, keeps on removing, keeps on removing. Here we can see the last steps of our iteration. So here you see this is the last failing input. It first tries to remove 4 equals, which actually is successful. Now we only have 6 characters left. Now it removes the first half of the input, the opening bracket. This doesn't work, it passes. It takes away the second half in here. This passes again. So it takes away smaller parts, namely the first digit. And now we have another failing input. And it keeps on removing one character after the other in the very end. This is how small the granularity has become, until the last failing input is just the opening and the closing parentheses. And we already know that this input cannot be reduced any further, because if we remove the second character, then this passes. And if we remove the first character, then this passes too. Actually, the input, the reduced input that is returned by delta debugging is guaranteed to be something that is called one minimal. One minimal meaning that if you remove any single character from this, from the reduced input, then the failure will no longer occur. Every single character that is in there is actually relevant for the failure. So this takes 29 tests, so it keeps on running and running and churning and churning and is happy, and in the end, boom, we have reduced the whole thing to just an opening and a closing parenthesis. Now, this idea of removing smaller and smaller parts from the input is actually something that at first sounds straightforward, but the nice thing about delta debugging is that it automatically adapts to the input, in that it first tries to remove large parts, which can be very effective if the input is due, if the failure is due only to a small subset of the input. And by adapting the granularity to first remove larger parts and then to remove smaller parts, it's particularly effective. We could also go and say we simply are going to remove one character after another, but if you then have an input of whatever, 100k characters, then you're going to have 100,000 tests, which is typically far too much. We could also go and do just binary search, but just binary search may not be sufficient if the failure conditions are distributed over both halves. And the nice thing about delta debugging is that it starts with binary search, which is very quick, very efficient, logarithmic complexity, and only at the very end boils down to removing one character after the other, which is linear complexity. And this algorithm is being considered one of the most successful automated debugging algorithms ever. You will find it in lots and lots of applications, sometimes not even under that name, because it has found its own life after time. A typical application, however, is with fuzzing, because in fuzzing you first generate long strings, complex inputs, and as soon as you have a failure, you have these synthetic inputs which mean nothing, which are full of weird characters and all, and then delta debugging helps bringing it down to a minimum. So one of the reasons that I'm particularly excited about delta debugging is because I'm biased. I'm the inventor of the whole thing. But the effect of delta debugging is indeed pretty large. So when I designed this algorithm and I published this whole thing, This was a few weeks after we had published it. I got a call from Microsoft. This was from the SQL tester group. That is the group that tested SQL Server. And they had developed a fuzzer, a grammar-based fuzzer, to actually produce long SQL queries, and found that some of these SQL queries would cause the server to crash. And then they submitted bug reports and told the team, if I have this super long and complex SQL query, your server is going to crash. And the SQL Server team would say, yeah, but nobody ever issues these queries. So we don't care. Thank you. And so they came to me and asked me, hi, Andreas, we'd like to apply your algorithm. Would you have maybe a C# implementation that we could run it? And I said, C#? No, I don't have C#. All I have is a Python implementation. And actually, this Python implementation is pretty small. This is certainly one of the shortest algorithms ever published. Let me see whether I can find the implementation. This is the exact. What we see here is the exact code that I used in time. Here we have it. This is the delta debugging reducer, and this is all there is. This is about 20 lines of code. This is the reduce function, and I was always proud to have designed an algorithm whose implementation, mind you, implementation would fit on one single slide. So this is the actual algorithm that goes through things and reduces things. And you can study this at your length. So what happened here was I sent this algorithm to the Microsoft team, and they said, yeah, well, that's Python, right? Yep. We don't know Python. Yep, that's your problem. Okay, good. Still, we're going to do this. 4 hours later, I got an email from them in which they told me, A, they had learned Python. B, they had got my algorithm to run. C, they had run it on some of their SQL queries. D, they had reduced these super complex SQL queries to just one line. And E, the SQL Server team is panicking. Yep, that was the entire story. Because sure, if you come up with some super long and complex input, you're not going to convince too many people. But if there is just this tiny thing and it already causes a crash, oh man, this is general. This could happen anywhere. What are we doing? Oh man, panic. Yep. So this is one of the stories that where delta debugging changed things. And of course, the SQL Server team since then has always used delta debugging to reduce their failure-inducing inputs. Classic. Also a tip for you, of course, because if you use fuzzing, don't go and send people these super long complex inputs. Send them the shortest thing that is available first, out of courtesy. Second, you're going to be way more effective with that. Okay, that was my short story. In the chapter, you're going to find not only an implementation of delta debugging, a very short implementation, we also have something more complex for you just because we can. Namely a grammar-based variant of delta debugging, which uses the grammar to reduce things, which of course is more effective because that's when you can actually go not only by characters, but you can take out entire syntactic entities of the input, making things faster, making things possibly more precise. But also comes with a much larger overhead. So instead of 20 lines, all of a sudden you're going to have 400 lines. But, well, you can try this out at your leisure. Yeah, but that's the entire story of delta debugging. And that's also why I would always recommend to not only fuzz, but also debug afterwards, such that your bug reports have the greatest possible effectiveness. Enjoy the read, and thank you very much.